Let's talk about Green's theorem. So Green's theorem says that we have a positively oriented closed path C in our domain D. And by the way, our domain D has to be a plane region now. So let me just sketch a region here. We have a region of the xy plane, so there's the xy coordinate system. And our domain, or our curve C, our path C, has to be a Jordan curve. So that means that it has to be a simple closed curve. It can be a little crazy at times, but it cannot overlap itself and it cannot have endpoints. And so in this situation, the curve C is closed, it's simple. Another name for that is a Jordan curve, and this curve is positively oriented. And so the positive orientation means that as you travel around the boundary of the curve, the interior of the curve, the bounded region bounded by the curve is always to your left-hand side. If you were to imagine being a small particle that's driving along or walking along the edge of this path, you would see the region, the pink region here, the magenta region to your left. Okay, in this setup we're going to need this bounded region. It's going to be part of our theorem, and so that bounded region is going to be called D. So that's our domain D. And frequently what we end up doing is we want to show that the curve, or the path C, remember the path C is this one, we want to be able to write down a relationship between this path C and the region D that it bounds. And so in this relationship, the path C is the boundary curve of D, and in math we frequently write this curve as partial of D, but not partial in the sense of a derivative necessarily, but definitely the partial in the sense of the boundary. So this is the boundary, C is the boundary curve of D. Okay, everywhere on this domain D we also want to have a vector field F, and this vector field F has component functions P and Q. And this vector field has to be differentiable in the sense that P and Q each have to be differentiable, and their first partial derivatives have to be continuous. Okay, and so then what does that mean? That means that at every point on this entire domain, including the boundary, F assigns a vector, right? So I'm trying to draw arrows at every point. Some of these arrows are not the most beautiful works of art, but the idea is we have this vector field F that is defined all over the entire region D. And what we want to do in particular is, there's two different perspectives here, so this theorem is going to be a two-way street. But from one perspective, we would like to compute the path integral of f.dr around the boundary of this curve. Okay, this path. The path is the boundary, but the boundary of the region. And on the other hand, we would like to compute some kind of an integral of a function, an integral of a function over the surface D, or over the region D here. And Green's theorem tells us the following. So Green's theorem in particular, like I said, it assumes that the first partial derivatives are continuous for this vector field F. And so it says the following. Let me write the entire theorem here, including its assumptions. So we've already set this up, but let's rewrite it. So let's let D be a Jordan region. Remember, we've talked about what that means, right? But I'm going to say that this is a Jordan region in the plane. Okay, so that means that it's a two-dimensional region. So it's a two-dimensional region. And let's say that this is bounded by, the region D is bounded by the positively oriented. So the positively oriented path or curve C. And furthermore, let's let F be a vector field. I'll just abbreviate that VF, defined on all of D. That includes the boundary curve C, such that the first partial derivatives of the component functions of F are continuous. So the first partials of F, this means the component functions of F, are continuous. So as always in math, when we state a theorem, it's very important that we have all of the assumptions down. I talked through the assumptions, now I've written them down. In some ways, the discussion we had at the beginning was a little more precise because I abbreviated some stuff over here. But once these assumptions are met, then Green's theorem gives us the conclusion, okay? And the conclusion is the following. I'm going to write it over here. So the conclusion of Green's theorem is that the path integral of f dot dr around the boundary, okay, so the integral around, I'm going to write this as boundary d, even though we called this c, I'm going to call it boundary d of f dotted with dr. So this path integral, this is equal to the double integral over the entire region, okay, the double integral over the entire region of some function that's related to f. All right, but it can't be f itself because we don't know how to take a double integral of a vector field. So what it ends up being is that it's the double integral of the difference of the partials here. So it's going to be dq by dx minus dp by dy integrated up with respect to area. Okay, and so this is the conclusion of Green's theorem. Now, we're going to do a lot of examples as we move forward in the notes. I'm going to prove this theorem for a special kind of a region, not a region that looks like this where it's very squirrely, I guess, for lack of a better word, but this is a very exotic kind of region. So we're going to prove this theorem for a region that can be thought of as both type 1 and type 2 at the same time. Just to make sure that we can prove it for at least one region. But the main focus here is that we're going to want to be able to interpret this and to use it. And so to finish off this video, all I would like to do is explain the significance here of what's going on with these two different sides and how they can be equal. And so, or at least to draw some comparisons to what we're used to, right? So let's recall that we have two fundamental theorems now of calculus. The fundamental theorem of calculus tells us, I'm just going to draw this in picture form. Okay, the fundamental theorem of calculus tells us that if we have a function, and the function is nice enough that we can integrate it, right? So we have some function y equals f of x, and we want to compute the integral of this function between, say, a and b. So now this function, whatever the integral means, the function is along this interval, right? So the integral is along this interval. And we want to evaluate the integral here, right? And if we know an antiderivative, then this becomes a very simple task, right? So if we know an antiderivative of this function, say f of x is such that f prime of x is equal to little f of x, right? Then what happens? Well, this fundamental theorem of calculus tells us that we can restrict ourselves to not having to think about the function over its entire domain interval, but just think about it at its endpoints, right? And then this integral becomes just the difference of capital F of b minus capital F of a. All right, so we've seen that before. That's the fundamental theorem of calculus. Very, very recently, we have kind of extended that theorem to apply to path integrals. And so for path integrals, the situation is very similar, right? So now we've got, instead of a function, let me change the color of this because I want it to match the picture to the left. So instead of integrating over a line segment, we now integrate a function defined over, a vector field defined over a path from A to B, right? And if our vector field, so in this situation we have, like I said, we have a vector field defined along this path. And if our vector field now is such that it is conservative, right? If it's conservative and we have a potential function, then the fundamental theorem for path integrals says, hey, we don't have to actually integrate this along the entire path in this case either, right? We can just plug into the boundary points. And what we learn is that in this case, the integral along this path C of f dot with dr, this is just equal to the values at the boundary points, of the potential function, right? So this one becomes little f of b minus little f of a. Now, these two theorems are saying pretty much the same thing. They're saying that in certain cases, so when we either have an antiderivative or a potential function, we can reduce our idea of our integral from on the entire line segment to just being calculated at the endpoints or the boundary points. Okay? Now, both of these were integrals over one-dimensional curves. Line segment, some kind of curve either in space or in the plane. Green's theorem takes this idea and it just kind of jacks it up to 2 dimensions. So Green's theorem, the situation is a little bit different, right? So in Green's theorem we have a nice region, so a Jordan region. So a Jordan region, remember, is a region that's bounded by a Jordan curve. So the region is almost defined by its boundary, but let me draw the curve just to keep the colors the same. We drew kind of wacky curve to begin with, but this is a legitimate Jordan curve as long as it truly meets right there. And so this curve I'm going to call boundary D or C. All right, and this has to be positively oriented. So positive orientation is easy to understand for a very round looking region. Even this one is not too hard to understand, but just remember that the region always has to be on your left hand side as you navigate the path, right? So there's our boundary. This is a perfectly fine Jordan region. The interior here, the region itself, is the interior, right? So the region itself is the shaded part here. It's all of this. And all right, I drew such a complicated region it took me a while to shade it, right? But there's the region D. And now along this entire region we have a vector field. So at every point, including along the boundary points, right? So there's a vector attached. If we think of a vector field as attaching a vector, it's attaching a vector at every single point along the boundary and the interior everywhere, right? And so the idea here is that if we want to compute the double integral of, so there's two ways to think about this, right? But the double integral over the region D of the function that we get by kind of taking, so in this scenario our vector field F has component functions P and Q, right? And if we take the difference of the partial derivatives in a way that looks very similar to our test to check that if a vector field is conservative, and that's not going to be a coincidence, okay? But if we compute, say, some function f little f of xy by just taking dq by dx minus dp by dy, all right, and this is now a function defined on our region D. If we then try to integrate that up, so dq by dx minus dp by dy with respect to area, then what Green's theorem says is actually we do not have to integrate over the entire region. This region might be very complicated. Maybe the boundary is actually easier to understand. Maybe we can parameterize the boundary easier, and maybe the vector field itself behaves in a more regular way along the boundary. And in this case, we can just, instead of integrating all along the entire region, we can just go along the boundary, okay, and we can reduce our double integral on this two-dimensional region to a one-dimensional path integral, which ends up being f dot dr. And of course, if we want to write out the components of this, this becomes the integral, again, over c, I'll just rewrite this as c, of p dx plus q dy. That's what happens when you take the dot product here, okay? So the idea, again, is that Green's theorem it's very similar to a fundamental theorem. It allows us to reduce the dimension of our domain. Now, one thing here that we're going to find is that frequently with Green's theorem, it's going to be useful for us to think in the other direction. We're going to want to actually compute a path integral by converting it to an area integral. But this is a two-way street. Anytime you have an equal sign, it's a two-way street. Okay. All right, so I'm going to end this video here, and as we move on in the notes, we're going to, again, prove this theorem for a special case, but then do a whole bunch of examples, and I hope that it will be very interesting for all of us.